Hello, this is Hideo Kobayashi. Okay, let's move on to today's material. And today's topic is control engineering, number 2. And today I'm going to explain about Laplace transform and then Fourier transform. Okay, this broadcasting is Kobayashi YouTube University of Science and Technology. So today's topic is used in control engineering, not only in control engineering, but also in vibration and noise, sound engineering. This is fifth delivery. My name is Hideo Kobayashi, and part-time lecturer at Graduate School of Nagoya University. And also I'm doing running my company named Aito Company Limited. I'm doing engineering consultant, mainly vibration and noise, including environmental peripheral engineering field. So this broadcasting is from Odara City, Kanagawa Prefecture, Japan, to the world. Okay, let's go to next page. So 1, why has Laplace transform been used conveniently in control engineering and vibration engineering and noise and sound engineering? Usually we have differential equation with time t as a variable for governing their physical phenomena. Usually, to solve this differential equation is difficult, sometimes impossible to solve it. So we usually do Laplace transform, and we change variable t to a variable s. Here it's written operator s. Okay, by Laplace transform of differential equation, we can get algebraic equation for operator s. Then we solve this algebraic equation, not a differential equation. Then we get here solution of the algebraic solution fs. Then this is inverse Laplace transform. For this one, inverse Laplace transform is made. Then we get a solution ft. We usually do this procedure in engineering, okay? But it's here, a normal direct solution. It's written, but it's, as I said before, usually very difficult or sometimes impossible to do it. So this way we don't use so often. We don't use this way. And we use this way, Laplace transform, and we do inverse Laplace transform of the answer. Then we get solution ft, okay? And this is the relation between time t as a variable and operator S. Okay. Next page, we'll think about one input-output system. The system is here. So system is written, is expressed by HT. To HT, input XT is given. And from here, we get output YT, okay? So this relation, okay, in T domain, time domain, YT equals XT. And this is a convolution, HT, okay? A convolution is bothersome calculation, product addition. We repeated that product addition calculation many times. So bothersome. So to avoid this bothersome, we Laplace transform YT, XT, HT. So we can think it only in S domain. Then we can write YS equals XS times HS. Only one product, by only one product. And product once, by calculation once, and product calculation once, we can get output in S domain. Okay, then we substitute J omega to for S. Then we can get F domain result. YF equals XF times HF. Okay, F is a frequency. Okay, so usually these are called frequency analysis, Fourier analysis. Fourier analysis. This is called Laplace transform. This is called Fourier transform. Okay. So we get into further in math. Number 2, what is Laplace transform? Laplace transform. Okay, why do we usually use Laplace transform? And definition of Laplace transform is this one, Formula 1. Okay, Ft, Laplace transform of Ft is written like this. Then Laplace transform is made. Then we write capital letter F, using capital letter F, Fs, okay? Then this Fs is obtained by this calculation. Integral from 0 to sigma Ft times e to the power of minus St and dt, okay? And where S equals sigma plus J omega. Sigma is greater than 0, always. J is imaginary unit. And sigma is called damping factor. Omega is called angular velocity or angular frequency. Omega equals n pi f, 2 times pi times f frequency, okay? The Formula 1 is called Laplace transform, this one. The Laplace transform of Ft is written like this. And next page. And substituting S for J omega, S equals J omega, the formula 1 becomes the formula 2, this one. Okay. So this formula 2 is called a Fourier transform. Okay. So Laplace transform is very similar to a Fourier transform. I'd like to talk about it more in next page. Next page. Okay, next page, 3. First, we think about frequency analysis using FFT. FFT means a fast Fourier transform. Okay. Suppose we have this signal and noise, electrical noise. Then these two are added. Then I hear, right, synthesis. Synthesized signal becomes like this. This contains this sinusoidal sine wave has noise. Then the figure becomes like this, for example. Okay, horizontal axis is time t. Then frequency analysis is made for this signal, synthesized signal. Okay, then we can get this kind of frequency analysis. Okay, when we do Fourier transform for this synthesized signal, then we can get this one, frequency analysis. Usually, this is done by using FFT analyzer. FFT analyzer. I'm going to next. 4. Fourier transform and Euler's formula. So as I explained, frequency Fourier transform is expressed by this equation, number 2, where e to the power minus j omega t is called a phasor. This works as element and to make rotation. Then, by the way, Euler's formula below works as rudder. This one. This one is Euler's formula. So when I explain Euler's formula, number 3 equation formula, in the diagram, a figure, okay, figure 3, we can get figure 3, okay. And this is a complex plane, horizontal axis, real number. The vertical axis, imaginary number. Okay, 1j, minus 1 minus j. Okay, and from here, we do the rotation. Theta equals omega t, omega times t. Okay, then. And this point comes to this one, okay? This is written cosine omega t minus j sine omega t, okay? This is quite the same as this one. And this one is expressed by this one. And this one is in the formula of Fourier transform, number 2 here, okay? So this one, as for the magnitude, this one is only 1 as for the magnitude, okay? So just rotation. So Ft, the magnitude Ft is still Ft. Then this is changed to rotation. Then the time t variable becomes frequency f variable. Okay, we'll think a Fourier transform more. Suppose ft equals at. The value of the Fourier transform doesn't have unique value and goes to infinity. This means that the Fourier transform is impossible. Depending on ft, what kind of ft comes to the formula of Fourier transform. There are occasions that the Fourier transform is impossible. Sometimes possible, but sometimes impossible. Okay. This is that the Fourier transform is unbounded in mathematics. In this case, first, the Laplace transform is performed. Then S equals j omega is done. By this procedure, the Fourier transform, okay, I forgot to write transform here. A Fourier transform is performed without mathematical and theoretical problem. Without problem. Okay, so if we want to Fourier transform from ft, then first we do Laplace transform, okay, for ft. Then we do S equals j omega. Then we can get Fourier transform. So when we want to do Fourier transform in engineering, at that time, first we do Laplace transform. Then we do S equals j omega. Then we get Fourier transform. This is a procedure to do Fourier transform in engineering. Oh, sorry, I forgot to explain this slide. Okay. In the continuation of this slide, next one, I didn't explain. So now here I explain this slide. According to the Formula 1, Laplace transform is transformed as follows, okay? Laplace transform. So the operator S is used. S is equal to sigma plus j omega. So then we write sigma plus j omega instead of writing S, okay? Then we do like this. This one becomes ft times e to the power minus sigma t times e to the power minus j omega t, okay? So exactly speaking, we have to say, for example, this one, e to the open parenthesis minus j omega t, close parenthesis, but it's bothersome to say. So I say here, e to the power of minus j omega t, or e to the power open parenthesis minus j omega t is the way I use, okay? And here, this is one, e to the power of parenthesis minus sigma t, this one, sigma is equal plus value, okay? According to the definition. So this becomes monotonic decrease function, okay? So this is the damping factor. So this is never fail to have a value as a result of this integration. Okay? And also this is a Laplace transform. So we do first Laplace transform. Then we give S for omega t, only this one. So this disappears. Then this equation is called a Fourier transform. Okay? In Fourier transform, this one is equal 0. But in Laplace transform, this one lower limit for the integral is always minus infinity. Okay? But in Fourier transform, in Laplace transform, this is always 0, not minus infinity. Okay? Then suppose yt is 8t and t is greater than 0 in this situation. So no signal t is less than 0. Okay? If t, suppose if t is an arbitrary function in Fourier transform, but for example, even if t is like this, so simple one, this cannot have value, decided value, because as time t goes on, the area of this area goes to more and more and doesn't have unique value as for the area of this one. Okay, this explanation is written here. Okay, so we do Fourier transform for ft from the beginning. At that time, Fourier transform doesn't have unique value as a result of calculation of integral. But when we do first Laplace transform, then we do S equals J omega t. Then we can have the unique value. Okay? I explained this one before, already. So that's all for today's explanation. Okay, sorry. Today's explanation was not so good because I passed this slide in my explanation. After that, I add the explanation for this slide. So it's sometimes difficult to understand, and sorry. But today, this is what I wanted to explain. Oh, thank you very much.